we've talked about galaxies, we've talked about the structure of galaxies, the classification of galaxies. We're learning some of the evolution. There's a class of objects that I want to address. They're called active galactic nuclei. They are the core of a small fraction of all galaxies, and they include the most luminous objects known. And so I'd like to devote this lecture to understanding what we know about their nature, and we'll go rather quickly. So what are the known examples of active galactic nuclei? The first type of galaxy discovered to have something interesting going on in its center are a collection called Seyfert galaxies. These are typically spiral galaxies. And what's weird about them is first discovered, as most astronomical things are, in their spectrum. The spectrum of these galaxies exhibits very pronounced, broad emission lines emitted from the compact nucleus. And these emission lines are superposed on a very broad, non-thermal continuum. So this does not look like the collected radiation of lots of stars. That's not what's glowing over there. And it's not a collection of hot gas. There's something else going on, although there is a thermal component. And Seyfert galaxies are classified into two varieties. The type 1 Seyferts have very broad, you see here these emission lines. We typically expect absorption lines above a thermal continuum. What we're finding is emission lines above a non-thermal continuum. So these are something interesting is going on there. The width of the lines of type 1 Seyfert galaxies corresponds, we understand this broadening to be due to Doppler broadening. So some of the radiating material is moving towards us and blue shifted. Some of the radiating material is moving away from us. Hence the light is red shifted. And the radial velocities associated to the width observed in type 1 Seyferts are 1,000 to 5,000 kilometers per second. And type 1 Seyferts often emit hard X-rays. In contrast, type 2 Seyferts have narrower, still broadened emission lines above a similar continuum and no X-rays. The radial velocities associated to type 1 Seyferts are about an order of magnitude less, a few hundred kilometers per second. So these are galaxies where something near the center of the galaxy is emitting some kind of strange radiation. What are the other examples that I want to collect together? Next collection of examples are called radio galaxies. These were first discovered at the dawn of radio astronomy. The first map of the sky produced by the amateur Grote Reber. I encourage you to read his story. It's kind of inspirational. Found among the 3 or 4 brightest radio sources in the sky what turned out to be an extragalactic source in the constellation Cygnus. It was called Cygnus A. And today we have large arrays of radio antennas that allow us to produce precise images. This is an image of Cygnus A. You see the galaxy Cygnus A is, or the center of the galaxy Cygnus A is the bright dot here in the center. The pink records the brightest radio signal, and this is surrounded by 2 gigantic lobes, and at least one of them is connected to the galaxy by a jet. To give you a sense, an estimate for the size, the distance between these 2 lobes is 140 kiloparsecs, so many times the size of a galaxy. The observation of the galaxy allows us to take spectral measurements, measure its redshift. Cygnus A has a redshift of about 0.06. This gives it a distance of about 240 megaparsec. For the 4th brightest radio object in the sky, that's awfully far. And in particular, the observed radio brightness of Cygnus A can be then converted, given its distance, to luminosity in radio. And as you can see here, the luminosity in radio corresponds to about 500 billion times the luminosity of the sun. More to the point, in radio waves, Cygnus A emits about 3 times the total luminosity of the Milky Way across all wavelengths. With the development of better radio telescopes after World War II, many more radio galaxies were discovered, although they're relatively rare compared to other galaxies. And they too are classified by the spectra of the host galaxies. We have broad line radio galaxies, similar to Seyfert 1s. These exhibit a bright nucleus surrounded by a very faint halo. The galaxy itself is barely there to be seen. On the contrary, the narrow line radio galaxies are typically hosted by giant elliptical galaxies, and very often, as in this case, they are accompanied by lobes at the ends of jets, and these jets have all kinds of internal structure, as we've seen in previous situations where we saw jets, and the jets emit radio, visible light, and large amounts of X-ray radiation. So we have this hugely luminous object, radio galaxy. This is a characteristic luminosity. Second type of strange galaxy. Radio astronomy also gave us a third kind, and this third kind was, as radio astronomy developed, there were lists of radio sources, and astronomers went out to look for what they called the optical counterpart, trying to identify the radio source with a star or a galaxy or something they knew about. And a breakthrough came in 1960 when Matthews and Sandage discovered the optical counterpart to a radio source known as 3C48. That means it was the 48th entry in the third Cambridge catalogue of radio sources. And this had, now that they discovered, and this was some faint star-like thing that was in the correct position to be the counterpart to the radio, where the radio signal was coming from. And so once they had an optical thing, they again took a spectrum. And the spectrum was exceedingly bizarre. It was dominated by broadened emission lines riding a continuum, sounding a familiar pattern. But these emission lines didn't look like the emission lines of any known element. They didn't recognize what it was that was emitting these. Sandage is quoted as calling these the spectrum of this object exceedingly weird. It was termed a quasi-stellar radio source, or QSR, soon abbreviated to quasar. So this was the first of many quasars. The next, in 1963, was 3C273, the 273rd entry in the catalog. When the optical counterpart of that was identified and a spectrum taken, this led an astronomer called Martin Schmidt to take a close look at it, and he identified that this weird, unfamiliar spectrum was actually a very familiar spectrum. These were actually the Balmer series of hydrogen absorption lines, except here as emission. They were very familiar to astronomers. They had not been recognized because they were shifted to the red to a degree not previously seen. The redshift of 3C273 was about 0.367. This means that when the light was emitted, remember that redshift is related to wavelength by the observed wavelength divided by the emitted wavelength is 1 plus z, and all distances since emission have grown by this factor. That means that in the case of 3C273, when the light was emitted, cosmic distances were about 3/4 their current size. Furthermore, we can relate z to the Hubble constant by z is h0d divided by c squared, and so by c. And so we can plug the known value of the Hubble constant and the measured redshift to produce a measurement of the distance. And indeed, this quasar is 1,300 megaparsec away. It's a very distant object. We can use the observed brightness of the thing to predict a luminosity, and we come up again with 500 billion solar luminosities on the order. It turns out that while extremely bright, far too luminous to be any kind of star that we know how to construct, this is actually dim for a quasar. More typical quasars have luminosities on the order of 10 trillion times the luminosity of the sun. And so astronomers go around collecting measurements of these quasars, and they are the most distant objects measured to date, in fact, and the most luminous objects measured to date. And there's not an obvious mechanism for producing that kind of luminosity. In fact, there is a decade-long redshift controversy suggesting that these redshift measurements are incorrect, that in fact quasars are Milky Way objects of much more reasonable luminosities, and much shorter distances, and that for some weird reason, the way their physics works generates these crazy redshifts. Here we see the spectrum of 3C273 superposed on the spectrum of a nearby object, and you see these hydrogen lines that are marked here shifted into these broadened emission lines, well shifted to the infrared. Luckily, as we remember, when you Doppler shift
light, the ratios of wavelengths are unchanged, so it was possible to ascertain that Schmidt was in fact correct. These are the Balmer lines of hydrogen. So astronomers go around amassing a collection of these quasi-stellar objects or quasi-stellar radio sources, and it turns out that they are often accompanied by jets. They exhibit variability at various time scales, and once they learn how to find them, they find that some of them emit radiation in the infrared, some of them emit most of their radiation all the way up to gamma rays, and some of them emit lots of strong radio signal, and some emit a very weak radio signal. So we now have radio loud and radio quiet QSO, quasi-stellar objects, or sometimes radio quiet quasars, which when you think about it is kind of a contradiction. That's the history of the term. We deal with what we have. So understanding what these quasars are is very interesting. They're certainly not stars. We see here the spectrum of another quasar, and we see the broadened emission lines. We also see the continuum, and this looks nothing like a blackbody spectrum. Interesting puzzle. Before we go on to discuss what these quasars are, let's pause a minute to appreciate what it is that they tell us, because quasars are extraordinarily useful objects. They're the most luminous things we know in the sky, and therefore we can see them at great distances. In fact, they have been observed all the way out to a redshift of z equals 8.2. In other words, all the way back in the history of the universe to when distances were a ninth of what they are today. So much of what we know about the history of our universe is because we can see quasars, and we'll see how we use them. If you look at the distribution of quasars in distance, you have to make corrections for the expansions of the universe. We'll talk about that next week. But when you make the correction, you find that it looks as though there was a period in the lifetime of the universe when quasars were the most common, and that occurred at a redshift today of about 2, so when distances were about a third of what they are today. Exactly how long ago that is depends on your cosmological model, and we'll discuss that next time. But it looks as though early in the universe quasars were rare, and they are rare today. That's why we rarely see quasars in our cosmological neighborhood. They are mostly distant objects. When the host galaxies were identified and the redshifts of the host galaxies were found to match the redshifts of the quasars, the controversy over redshifts was finally laid to rest. These are indeed distant objects, leaving the question, how can they be so luminous? And these host galaxies turn out to mostly be large elliptical galaxies. Again, the role of the large ellipticals keeps recurring here, and statistics suggest that in the lifetime of a galaxy, a given quasar event lasts only maybe a few 100 million years, and is often triggered by collisions or mergers with other galaxies, as we discussed previously this week. And but in the lifetime of a galaxy, perhaps a quasar can recur. So you can have a quasar, and then the galaxy will shut off the quasar, and then the nucleus will again become active. Before we go on to discussing what they are, let's pause to enjoy what these amazing objects give us as a window into our universe. So what is the great thing about them? The great thing about them is they're so luminous. They're not standard candles, but they're very luminous. You can see them at very large distances. What's great about a very large distance? Well, the first thing that's great about a very large distance is that things that are rare are more likely to happen over very large distances than short. So, for example, if you're looking for a galaxy cluster to lie along the line of sight from you to something, the farther the something is, the more likely that is to happen. And so the first examples of gravitational lensing were indeed observed when we found multiple images of a quasar lensed by an intervening massive object. This is one of the most famous examples, the Einstein cross. The symmetries of the lensing mass caused the quasar to be lensed into 4 distinct images. Spectral analysis shows these are 4 copies of the exact same quasar lying behind a foreground galaxy. And so quasars are useful as lensing objects. If you're looking for lensing events, quasars are good. There's an even better use for quasars, because their light is not only coming at us through large distances, but as I mentioned, through long times. This is light that has been around for billions of years, traveling through the universe and interacting with whatever was in the universe throughout this time and throughout the long distances. And so, in some sense, the light from a quasar is like the ice cores that we drill in the Arctic, because it bears the traces of whatever it encountered in the universe throughout its travels. What does that mean? Let's make that real. Here is the spectrum of our friend, a particular quasar at a redshift of 0.16. We have rescaled the wavelength so that the peak is at the emitted 1230 angstrom wavelength, at which this particular spectral line is actually emitted, and we see the continuum and the absorption line above it, and we see some the emission line above it, and we see some absorption lines. And identifying these absorption lines becomes an interesting exercise. There's a hint when you look at this more distant quasar at a redshift of 3.6. We've rescaled wavelengths so that the emitted wavelengths agree. So this is the wavelength at the time of emission. And we see that the absorption lines in this case form a dense forest of absorption. What is going on? Which elements absorb at all of these wavelengths? It turns out that, of course, there's only one relevant element. It's all hydrogen. But hydrogen only absorbs at one wavelength. Yes, indeed. However, as this light from this distant quasar was proceeding through the universe at discrete intervals in its billions of years of traveling towards us, it encountered clouds of hydrogen. And each cloud of hydrogen was encountered at some particular redshift. So the light that was absorbed at the hydrogen absorption Lyman alpha wavelength has been redshifted, is missing at a wavelength that's redshifted corresponding to the time at which the light beam interacted with that particular cloud. And so by tracing the times or the wavelengths, the redshifts at which there are dips in the spectrum, we can basically trace where along its path this light beam from the quasar interacted with clouds of hydrogen, and by tracing the depths of these absorption lines, we can trace how large or how dense these clouds were. And so in a very real sense, this is a cross-section of the universe over huge distances. This is one of our best measures of how much hydrogen there is. And remember, how much hydrogen there is, most of the hydrogen, it turns out, is not in stars and not in galaxies. It's in these large hydrogen clouds. How do we see them? We see them through the Lyman alpha forest. This is one of our best estimates of the total amount of hydrogen in the universe, which is basically the total amount of everything. And so in this sense, quasars are extraordinarily useful objects. And then the last thing is, because we can see them at various times into the past of the universe, they allow us to try to understand things like the evolution of galactic structure and maybe even of cosmology over long time scales. Pretty awesome things. But what are they? Well, before we turn to understanding quasars, let me introduce one other kind of strange object. One of the characteristics of the objects that I've discussed so far is that their luminosity varies at various wavelengths over various time scales, running from minutes for some of the X-ray flickering all the way to years. And here are some examples. So this is the luminosity in X-ray of a Seyfert galaxy. We see changes over hours. This is the luminosity of some of the spectral lines of a Seyfert galaxy. And below, we see the integrated luminosity of the continuum and in the ultraviolet. And what we're seeing here, if you look very closely, is there are variations over, say, days or weeks, and the variations of some, but not all, of the spectral lines follow the variations of the continuum with a lag of maybe a couple of weeks. What are we going to understand from that? Well, the interpretation is going to be that the continuum, the very bright, most of the luminosities in the continuum as always, the bright continuum radiation is ionizing the gas that is subsequently emitting these emission lines, and the time delay between this peak and this peak measures the distance from whatever is producing this to whatever is producing that. We'll get back to that. Blazars, of which this variable spectrum is a typical example, exhibit the same kind of variability. In fact, the original archetype, this particular blazar was originally misclassified as a variable star, so they are compact objects with variable luminosity and a non-thermal continuum, but very faint spectral lines, if any. And just to complete the picture, this is the variation in the luminosity of a quasar. Quasars also exhibit the same kind of luminosity. These are all, I claim, related phenomena. Blazars almost always exhibit jets, and the jets exhibit a phenomenon called superluminal motion. Superluminal motion? Really? Didn't I just finish telling you last week that superluminal motion is nonsense and acausal, and there is no such thing? Well, I mean apparent superluminal motion. And apparent superluminal motion is certainly something that happens and something that we can understand. So imagine that over here is our eye looking from Earth at an object which is emitting radiation over here, but also moving not quite at us, but at a rather small angle theta to our line of sight. And imagine that a time delta t passes, so the object is moving with some velocity v in this direction. It started here, and after a time delta t, it's now over here. And imagine that v is significant compared to the speed of light, so we could make relativistic corrections to all of this, but it's not going to be that crucial for us. We're working in r frame, and this is the motion that the object does. If we look at the object, what we will notice is that its line of sight is changing. We first saw it here, and then later we saw it here. We would measure this angular motion, convert it to a measurement of what I call the tangential velocity, and if we know the distance to the object over here, we would multiply it by this angle and set that equal to vt delta t, and that's how we would compute the tangential velocity. And what apparent superluminal motion refers to is that when you do this calculation, the computed value of vt turns out to be bigger than the speed of light. How can that be? Even though v is less than the speed of light. How does that work? Well, it works because if you think about it, the light emitted at this point, and the light emitted at this point follow these two blue trajectories to reach our eyes. Because the object is moving towards us, the light emitted here takes a shorter time to get to us because the object has come closer. By how much? Well, by approximately, to a good approximation, this distance, d. What that means is that the time between the observation of light beam number 1 emitted here and light beam number 2 emitted there, well, the time in their observation is given by what? Well, light beam number 2 was emitted at time delta t after light beam number 1, so obviously delta t. But then light beam number 1 had a longer way to go, so it took some extra time, so I need to subtract that off. And that is just d over c is the extra time it took light beam number 1 to traverse the extra distance. Now, what is d? Well, d is, if theta is very small, d is of order v delta t. Now, if you want to be accurate, there's a cosine of theta there, but we don't do trigonometry. So this is of order delta t times 1 minus v over c when I plugged in that d is v delta t. Oh! So when we measure the angle alpha that the star moved and divide it by the time over which we notice that motion to be occurring, we are not dividing by the actual time between the two events by a factor of 1 minus v over c. That factor can be quite small if v over c is significant, and as a result, we can conclude that the object is moving faster than light if we fail to take this into account. So superluminal motion is not something that happens. Apparent superluminal motion is characteristic. Here's the example. This is quasar 3C279. We see here the quasar. We see the knotted structures in the jets. We see the jet moving off to the right over a few years. If you set the scale, take the distance to the quasar, you would discover that the motions of these dots correspond to moving faster than the speed of light, at about 3 times the speed of light, in fact. But the reason that this is happening, we now understand, is that this light we observed in 1993 and this light we observed in 1994 may have been emitted 7 years apart because of the factor 1 minus v over c, because this jet is approaching us at relativistic velocities. So apparent superluminal, no contradiction with relativity, no problem with causality.